As a group, we looked into the variation of the Monty Hall problem called Let's Make a Deal.
Let's give a quick overview of the way the game is played. So first, there are two people involved, a contestant and a host. The contestant is shown 3 closed doors with prizes behind them. Each prize can be ranked with numbers, 1 being the worst and 3 being the best. The contestant does not know the prizes or their rankings beforehand, and therefore must form their own opinions on such as the game is going on. The contestant begins the game by picking 1 door to open and is allowed to see the prize behind it. The contestant can choose to keep this prize if they believe it is the best, or they can move on to the next door if they think the best prize is behind one of those other 2 doors. If the contestant moves on to the second door, they cannot go back and take the prize from the first door. They can, however, use the prize from the first door to determine the rankings so far of the prizes.
Question 1 asks how the contestant can get a 50% probability of winning the best prize when there are 3 doors in the problem. The contestant should begin by choosing the first door, looking at the prize, and then moving on to the second door. The contestant should immediately move on to the second door because each door has a 1/3 chance of having the best prize behind it. So the first door opened only has a 1/3 chance of being the best prize, while the other 2 doors combined have a 2/3 chance of being the best prize.
After opening the second door, the contestant should form an opinion on whether the prize behind door 2 was better or worse than the prize behind door 1. As the contestant moved from door 1 to door 2, there were only 2 options that could happen. The prize would get better or the prize would get worse, and each of them held an equal probability of 50% that it would happen. This 50-50 chance can be represented by listing out all of the possibilities of arranging the prizes 1, 2, and 3 in different ways, which is equal to 3 factorial. There are 6 options, and the 3 on the left that are highlighted in green show the 3 out of 6 that have the second prize being better than the first, and the 3 on the right show the second prize being worse than the first.
If the contestant determines that the prize behind door 2 is better than the prize behind door 1, the contestant should stay on door 2 and choose that as their final prize. Out of the 3 options that showed the second prize being the better than the first one, only one of the 3 has the third door holding a better prize than the second. We don't worry about if that is a better chance than what is behind door 1 because the contestant can no longer choose that option. 2/3 of these options is what is behind the second door better than what is behind the third door. So the contestant has a better chance of getting a prize, so if they stay with door 2 in this instant. If the contestant determines that the prize behind door 2 is worse than the prize behind door 1, then the contestant should switch and move on to door number 3. Of the 3 options that showed door 2 being worse than door 1, only one option has the prize under door 2 being better than the prize behind door 3. There are 2 out of 3 options that result in the prize behind door 2 being better than the prize behind door 3. So in this case, the contestant should switch behind and choose door 3.
Now we looked at this problem with 4 doors instead of 3. The question asked what the percentage of the amount of times that the contestant would win the game using the strategy that we found out in question 1 was. The answer we found was 42%. After listing out 4 factorial, or the total number of ways to arrange the numbers 1 through 4, we went through and used the strategy. For example, for 1, 2, 3, 4, we opened door 1 and found prize number 1. Then we would move on to door 2, which held prize number 2, and realized that the prizes were going better, and stopped at door 2 to choose that prize. Another example would be 3, 1, 4, 2. We would open door 1 to find prize 3. We would move on to door 2 to find prize 1, which is worse than prize 3, so we would move on again. Behind door 3, we would find prize 4, which is better than prize 1, so we would stop and choose that prize. After going through all 24 numbers, we found that 10 would result in a winning prize for the contestant, and 10 out of 24 is roughly 42%.
For 4 doors, we looked at the step-by-step choices to see if the strategy was still correct for 4 doors. After picking the first door, move on to the second door. If the second door was worse than the first door, out of the 12 options that resulted in the prize being better, there were 7 that had prizes under door 3 that were better than door 2. So the contestant should switch to the third door to have the best possibility of getting a better door. If the prize behind the second door was better than the prize behind the first door, out of the 12 options, 8 have the prize behind the second door being better than the prize behind the next, while only 4 have the prize behind the third door being better than the second. So the contestant should stay on the second door and choose that prize.
After the prize got worse, we said to move on to the next door. Now, if the next door is worse again, this time worse than the second door, then the contestant should move on again. There are 3 out of 24 permutations that have the order of the numbers get worse, then worse again, but only one of these 3 gets worse again. 2 out of the 3 options have the prize behind the last door being better than the previous door. The contestant should follow the pattern and switch again and choose the 4th door as their prize. Now, if the next door is better than the second, then the contestant should stay. There are 7 permutations that have the order of the first present going worse and then better. Then out of these 7, only 2 have the 4th door being better than the 3rd. 5 out of the 7 doors have the better prize being behind the 3rd door.
If the situation were to switch to 5 doors and 5 prizes, the same strategy could be used. 5 factorial is 120, so there are 120 possible arrangements of the number 1 through 5. Out of these 120, 41 resulted in a win for the hypothetical contestant, which is about 34%.
The same solution used for 3 and 4 doors was used to figure out the percentage for 5 doors. The first door was picked, then the second, then if the prize got better, the contestant picked that prize. If the prize got worse, the contestant moved on until the prize got better, and then chose that prize.
Using the results from the problems with 3, 4, and 5 doors, we found a pattern in the data. With 3 doors, the contestant had a 50% chance of winning. With 4 doors, there is a 42% chance of winning. With 5 doors, there is a 34% chance of winning. We realized that starting from the 3 doors and using that as the 0, that each time a door was added, the percentage went down 8%. This meant that since 5 is 2 more than 3, the percentage would go down 8 times 2, or 16, which it did. To have 3 doors and 50% as the 0, we had n minus 3 be a part of the equation, and also the starting value was 50. 50% minus the difference of 3 subtracted by the number given, multiplied by the 8% gave us our function. F of n is equal to t minus 8 times the difference of n minus 3.
These are the sources that we used to gather this conclusion, and we also received additional help from Ms. Collier and Mr. Wurst. Thank you for watching.